Good morning, afternoon, or whatever the heck it is where you are on this fine and dandy Tuesday. Welcome to another edition of Takeo Tuesday. I'm John Barba, along with Dave Holdorf and Jason Cox, and a parade of dozens. We are doing this live from the Takeo training room today, and Dave is joining us live from Famous Supply out in Ohio. Dave, where are you at? What's your deal?
I'm just outside of Cleveland right now and doing a full day training session at the Hydronics Symposium, the fourth annual that Famous has done out here. So if you are nearby, hurry up and get here. I still have 4 more classes to go this afternoon. And if you're near the Pittsburgh area, I'll be there tomorrow.
Cool. Traveling Dave. Well, I'm here at the Takeo factory in Cranston, Rhode Island, and I'm looking at a sea of about 7 faces. No, we got the early arrivals here. Where are you guys from, by the way? You're from Albany, right? Newburgh, New York. All right. So we got the upstate New York and Western New York coming in buses. These guys got here. They were here about 9:15 because they heard we're such a great show. They wanted to get a really good seat. So they're here early. We've already had lunch. Buses coming in just a few. So we've got a live audience today for Takeo After Dark, which is kind of exciting. And I thought that would get a round of applause from this group, but apparently not. There we go. And Jason's just having breakfast out in his living room, which is
in not so sunny California this morning. We're socked in with some fog, and it's welcome. It's welcome. It's been pretty hot out this way.
All right. Well, cool. Well, hey, today we've got Dave and Jason are going to monitor the questions. And I'm going to rock and roll on the presentation. So let's get started with this. And today's topic is heat loss for hydronics. A couple of words of warning.
Started,
say again? Oh, you know what?
You need to share your screen.
How about that? I'm out of practice here, Dave. I do need to share my screen. How about that? All right, here we go. There it is.
That's not it.
That's not it?
That's just part of the PowerPoint, not the slide deck.
No, hold on a second. Hold on 1 second. Give me a moment.
Yes, people. Oh. Yes, people, this is our first time doing webinars. We've never done these before, so those are joining us for the first time. I'm kidding. This is just out of the element of our normal home offices.
There we go. How's that? Better?
Nope, still see the same thing.
Still seeing the same. Son of a gun.
We're seeing the PowerPoint program.
Oh well, then let's fix that. I am in the. There we go. Go my screen clean. How's that? Better?
There you go.
All right.
Now you're good.
Give me 3 whacks at anything and I'll get it, Dave. Just leave that alone. All right.
Yep.
Okay. Today's topic.
Thanks for your patience, everybody.
All right. Thank you, everybody. Now, these guys in the audience are saying this guy knows what he's doing. I'm not. I have my doubts. But anyway, we're talking about heat loss for hydronics today, and this is a subject that, again, like many, is near and dear to my heart because nobody teaches heat loss anymore. It's one of those things where since the advent of apps, nobody really wants to teach, or nobody does teach what goes into making that app do what it needs to do. How do we arrive at a BTU load for a house or for a room or a zone or whatever? All too often we kind of drop to that, let's figure 30 BTUs a square foot or 35 BTUs per square foot. It's good enough. It'll work. Yeah, it will. It will. If you figure 30 to 35 BTUs per square foot for your heat loss, it's going to work. You're going to heat that structure. But it's kind of, in my mind, it's kind of like doing finished carpentry with a sledgehammer. All right. Hey, Dave, you might want to mute your microphone there because I'm getting a lot of vocals from the background. It's kind of like doing finished carpentry with a sledgehammer. You can do it. The wood will stay together, but you don't have a real pretty finished product, do you? They make specific tools to do finished carpentry because it requires some precision. Heat loss for hydronics is the same thing. We're as in our trade, we're very concerned. The thing that scares the hell out of us, and I think you guys here will agree with me, the thing that scares the hell out of you isn't having too much heat, It's having not enough heat, right? That's the thing that keeps us up at night. That's the thing that we're worried about. I don't want that phone call. We're going to give them enough heat. There's a difference between enough and overdoing it. The problem with the challenge is that there's no immediate downside to oversizing. So your heat loss calculation is way overboard. You way overdid it. There's no immediate downside other than maybe you're buying a more expensive boiler than you need to. You've got bigger pipe. All of that stuff's more expensive than it needs to. But that's really the only downside in the short run. In the long run, you've got a system that's nowhere near as efficient as it could be or should be just because we overstated the heat loss. We've got a system that we're going to promote short cycling with the boiler. If the heat load's only 40,000 BTUs and we put in a 200,000 BTU boiler, I'm sorry, that boiler's never going to have time to get really efficient. And when you oversize to those extremes, a couple of bad things happen. First off, we short cycle, which does kill efficiency, but short cycling also prematurely wears out moving parts, and we have service issues long before we really should have service issues in the system. So oversizing covers you in one aspect, but it's not the right thing to do in the long term. So that's why heat loss is really where all of this starts, because we got to know the load, right? We've got to know the load. Now we're talking about residential heat loss today. So if we have a lot of guys out there in the audience that do commercial heating loads, there's the math is the same. It's just that this is a house. It's not a high rise. It's not an office building. It's not a data center or anything like that. It's a house. All right. We're not flying this thing to Mars. It's just a house for people to live in. Does that mean we cut corners and take shortcuts and use rules of thumb? Not necessarily. We're still going to go through this thing step by step and do it properly. It's just that, yeah, we may take a couple of shortcuts here and there to make the math easier, not to replace the math, but to make the math easier. So that's what we're going to go over today. Now we've got some folks out there in webinar land. If you could do me a favor, just go to your chat question section on your control bar and just say hello. Let me know where you're from and who you are, and just say hello. That way I know you can hear me, because there's nothing worse than doing a webinar and talking and no one can hear you. The only thing I think worse than that is having Dave walk you through how to get the PowerPoint back up again when you've done it a million times, but that's embarrassment in its own right. So, okay, we got a bunch of guys. We got Gilles from Montreal, bonjour. We got Steve St. Hilaire, what's up? All right, more you guys just chime on in. We do appreciate just you guys just letting us know who you are and where you're coming in from. And please be sure to ask your questions. Any questions you have, type them on in, and we're happy to do our best. Jason and Dave will be monitoring those questions. And you guys out there in the studio audience, you got any questions, just fire away too. If I'd like it, I'll answer it. Just kidding. All right. Okay. So let's get this thing rolling. Boy, we got Winnipeg, Manitoba. We got Corey from McCoy Sales out in Denver. All right. Excellent. We got Henry from Baton Rouge. Great to have people from all over the country. Thank you so much. All righty. So hydronics in general and heat loss in particular requires this acronym, RTFM and DTFM. RTFM and DTFM. Real important things to write down if I were a note-taking person. RTFM stands for read the free manual. Every piece of equipment you buy has a free instruction sheet in it that comes with it. And I think read what it says. It's amazing the stuff you'll learn. That's RTFM. DTFM is a little bit different. DTFM is do the freaking math. The math will never lie to you. All right, the math will never lie to you, and the math isn't that hard. A lot of people in our industry are kind of concerned about math. They say, I don't like math. I'm not good at math. I firmly believe that we in the plumbing, heating, and air conditioning industry are a heck of a lot better at math than we think we are. Because math, if you think about math, why did they teach you math in school? What was their point? Why did they want you to find X? It's not that someone was going to come up to you in the street, hold a gun to your head and say, quote me the Pythagorean theorem, I'm going to shoot you. That's never going to happen. But why do they teach you math in school? Well, they teach you math in school Because it's structured step-by-step problem solving. What do you do out in the field every day? Structured step-by-step problem solving. If you're a troubleshooter, if you're going there for some sort of service, you have to do structured step-by-step problem solving. That comes from math skills that you may have hated to learn, but they are serving you well in the real world. It's not, a squared plus b squared equals c squared. That's nice to know, but it's not really that practical. But common sense, structured step-by-step problem solving is a practical application of that knowledge. Now, the math we use in hydronics, addition, subtraction, multiplication, division, we had that stuff mastered by 4th or 5th grade. Now it's just a matter of when you do it and where and how. That part's pretty easy, and we'll show you all that. But do the math. The math will never lie to you. And the math for us starts with heat loss calculations. We can't size a boiler. We can't size a piece of baseboard or a radiator. We can't figure out what water temperature to run for radiant. We can't size a boiler. We can't select a circulator. We can't do any of that stuff until we know a BTU load. If we do try to do all that without having a BTU load, what are we doing? We're guessing. We're guessing, right? And professionals don't guess. Think about a professional that you use in your day-to-day life. Let's say, I don't know, a doctor. Would you want a doctor that uses the tools that he has available to him to treat you the best way he can, or do you want him to just take a guess? This guy's body's a lot like the last guy's body. I think his appendix is right around here. Give me a knife. All right. I don't think we want that. We kind of like a little bit more precision with our surgeons. Same thing here. Got to know what we're doing and why we're doing it, and starts with heat loss calculations. Once we know that BTU load, we can get down to the serious business of properly sizing the pipe and properly selecting the circulator. All right. A lot of people say, I use ECM circulators. They size themselves. No, they don't. No, they don't. You need to know what they do and why. They're not smart pumps, they're obedient pumps. They will do what you tell them to do. So still, knowing the load, knowing the flow rate, knowing the head loss will allow you to select that circulator properly. Ultimately, our goal here, friends, and it starts with heat loss, is to put together a system as opposed to a collection of parts. We like to say in our training classes that it's easy to throw together a hydronic heating system. You throw in a boiler, you connect a bunch of pipes and pumps and radiators, keep the water on the inside, wire it up so it makes fire, and keep people from freezing to death. That's not that hard, right? That's not that hard to do. A reasonably competent handyman could do that. Why do people hire professionals, guys who have their company name on their shirts and drive a company van? Why do people hire professionals as opposed to reasonably competent handyman? Is because they want better. They want a professional installation done properly. A system where everything is chosen for a purpose as opposed to, this is the cheapest stuff I can find. I'm going to slap it together and get the hell out of here. That's not what professionals do. Professionals take a little bit more care in what they do. So that is the difference between a system, and a system is something in which the whole is greater than the sum of the parts as opposed to just a collection of parts. Cool. So let's talk about some heat loss fundamentals. All right, let's get into some fundamentals. Heat loss fundamentals. When we talk about doing a heat loss, again, that's arithmetic, right? We don't use rules of thumb. Somewhere along the way, over the past maybe 40 or 50 years, what was a rule of thumb has transformed into something completely unrecognizable. Rules of thumb used to be shortcuts that would help make the math easier. And I'm all in favor of shortcuts that help make the math easier. The problem is rules of thumb today have morphed into basically a tool we use to not bother to learn what we're doing. It's a shortcut that keeps us from having to know what we're doing. Well, I don't want to know all of this stuff. Give me a rule of thumb, 35 BTUs per square foot, all right? I always use this circulator, blah, blah, blah. Lots of rules of thumb when it comes to our world, and they have become replacements for knowing what you're doing. And that's unfortunate. That's unfortunate because professionals should know what they're doing and not rely on rules of thumb. So do we rely on rules of thumb or do we do the math? All right, do we do the math? I think doing the math, and we're not going to have any math that hard, solve for X. Okay, simple addition, subtraction, multiplication, and division. All right. Now, at best, heat loss is an educated estimation. We're taking measurements of an existing structure, or we're taking measurements off of a two-dimensional blueprint and trying to imagine what a three-dimensional finished structure will actually lose for heat, and trying to mathematically get as close as we can. So at best, folks, it is an educated estimation. And what we measure is air infiltration. That's heated air that leaks from inside to outside. It's replaced by cold outside air. We have to heat that air back up. That's heat infiltration, heat loss. We have heat transmission, or conductive heat loss, that just conducts through walls, through windows, doors, floors, ceilings, etc., through flat panels. That's heat loss through transmission or conduction. All right. Some heat loss terminology that we need to know. Looks like the buses showed up. Everybody's out there getting lunch. Very good. We're having tacos here, by the way, because it is Taco Tuesday and Taco Tuesday here in Cranston. So some terminology for you. First is ODT. ODT stands for outdoor design temperature. Now we like to call that the quote unquote coldest day of the year. We want to design our heating system to maintain, let's say, 70 degrees indoors when it's this coldest day of the year outdoors. This is one place where a lot of people will add a lot of unnecessary fudge to their calculations, where they say, oh, well, hey, this is New England, man, or this is Western New York. It gets pretty cold out here. I better design this house to stay warm at -20 just in case, because I don't want the phone call. Good intentions, but I think we're unnecessarily oversizing what we're trying to do here. So ODT will show you where to find that information, all right, where you can find some an accurate outdoor design temperature for your area and what it really represents. IDT, of course, is your indoor design temperature. That's the temperature you want to maintain indoors when it's that quote unquote coldest day of the year outdoors. So that's IDT. ODT is outdoor design temperature. IDT is indoor design temperature. And then you got DTD, which is design temperature difference. That's simply the spread between the ODT and the IDT. If you subtract ODT from IDT, you get the DTD, or the difference. So if I'm designing to a 0-degree outdoor temperature and I want to maintain 70 degrees indoors, 70 minus 0 gives me a design temperature difference of 70 degrees. That's important because that's our multiplier. We're going to use that when we do the math. All right. We're going to use that when we do the math. If I say, you know what, I'm a little scared of 0, I'm going to go to -10. Now it's 70 degrees indoors, -10 outdoors. Now that difference is 80 degrees. It's a bigger multiplier. I'm going to get a bigger number. I may not need that bigger number, but I'm going to get it anyway, because I'm exaggerating one end or the other. It's no different than if I went from, you know, I kept it at 0, but I moved the IDT up to 80. It's still a spread between the two. All righty. UV stands for U value. U value. It's not a measure of your self-esteem. It is a measure of a material's ability to conduct heat. Now, in the world of construction, do we want a high U value or a low U value? Well, generally speaking, because it measures a material's ability to conduct heat, we want a low U value. So the lower the U value, the better for wall construction, for windows and things like that. We don't want to conduct heat very well from one side to the other, because if we're conducting heat really well from inside the house to outside of the house, our heat loss starts to get out of control. So we want low U values. And U values and R values are kind of flip sides of the same coin. We'll explain what that's all about in a bit. And again, here's that IDT, ODT minus IDT thing. So again, 70 degrees indoors, 0 degrees outdoors. That would give you your design temperature difference. Now, that outdoor design temperature, I want to touch on that real quickly. That outdoor design temperature that is ASHRAE recommended, and it's ASHRAE recommended by ASHRAE 90A-1980. It doesn't represent the coldest it ever gets in a given area. It's actually the 97.5 percentile of cold. So what ASHRAE has done is they've analyzed weather data going back decades, and they say, you know what? 97.5% of the time over these decades, it doesn't get colder than this. So this is your outdoor design temperature. Now, does that make you comfortable? Designing to 97.5% of the cold is really what you're doing. Does that make you feel comfortable, or would that keep you awake at night? Good question, right? But think about this for a second. Let's say I do a heat loss calculation to that 97.5 percentile number, okay? So what that's saying is 97.5% of the time it doesn't get colder than 0 in this given area, but by definition, that means 2.5% of the time it does. I don't like that. If you do a heat load to that 97.5 percentile number and you do all your math diligently and you come up with a heat loss of 57,421 BTUs, what are the odds, ladies and gentlemen, of you A, finding, and B, installing a boiler that has an absolute net rated output of 57,421 BTUs? Slim and none, right? And Slim just left town. You're going to pick the brand of boiler you like, size up that covers it. And if the brand of boiler you like, size up that covers it, has a net output of 75,000, well, you've got about 18,000 BTUs or 17,000 BTUs sitting around looking for something to do under design conditions. So you're more than covered for those dips below design. As long as you got the horsepower in the boiler to get her done, you're going to get her done. So that's why the 97.5 percentile is kind of one of those numbers you don't get too wrapped up about. Otherwise, it's step one towards oversizing. Now, where do you find this stuff? The IBR H22 heat loss guide is a great place to, it basically has all of that information for you. All that information is there. They will give you all of the tables for R values and U values and construction, etc. And they'll give you a listing of all 50 states plus the provinces of Canada with recommended outdoor design temperatures for you. So this is an example of this is page 1. So it starts with A and goes right to F. Page 1 of the H22 heat loss guide outdoor design temperature chart. And let's take a look in Colorado. Denver, Colorado has a recommended outdoor design temperature of 1 degree. Now, I've been in Colorado when it was a heck of a lot colder than 1 degree. It just doesn't happen very often. Statistically speaking, about 2.5% of the time over the past 50 or 60 years. So that is the ASHRAE recommended outdoor design temperature for Denver. If we were to look at Fairbanks, Alaska, well, now we're looking at an outdoor design temperature of -47. I've been in Fairbanks, Alaska when it's been -47, and let me tell you, that falls under the heading of freaking cold. All right. Now, if I had the same house, exact same construction, everything, one in Denver and one in Fairbanks, it's pretty clear the one in Fairbanks would have a much higher heat loss. That's just because of where it's built and the type, and if the construction is exactly the same, it's going to lose more BTUs at -47 than it would at 1. So again, those are where the numbers come from. Those numbers after the slash that you see there, that represents degree days. And that's a tool that can be used to help estimate fuel consumption. Alrighty, any questions out there, Dave and Jason, that I need to address, or how are we doing out there, folks?
We are good. We just got our hellos and highs in, and not a question yet.
All right, very good.
Carry on, sir.
Alrighty then. So let's do a quick example. We're going to do this little room here. All right, this little room has 2 outside walls, 3 windows, and a little vaulted ceiling. All right, it's 8 by 12. Those are our dimensions. It's 8 by 12 with a vaulted ceiling that ranges from 8 feet on the low end to 14 feet on the high end. All right, so that's important to remember. 8 feet on the low end, 14 feet on the high end. Okay, and we have 2 outside walls, an 8-foot wall and a 12-foot wall, and we have 3 windows, and each window is 3 by 5, and they're all the exact same construction windows, so they're all the same type of window. So 3 by 5 windows, and the wall construction is 2 by 6. And we have R19 insulation in those walls and R38 up in the ceiling. Right? Because on the other side, it's a vaulted ceiling. The other side of the ceiling is the roof. The other side of the roof is outside. We want to make sure that we keep the heat in and not let it out. So R38 in the ceiling. The first thing we want to do here is get our dimensions. And how do we deal with a vaulted ceiling? Well, you can get into a lot of trigonometry and math if you want, or geometry if you want to. perhaps the easiest thing to do here is to simply square off the ceiling. All right, simply square off the ceiling. You're going to have a slightly higher wall heights, but a little bit smaller ceiling area. If you want a little bit of fudge, this builds in some fudge for you because we've got more wall area, which has lower R value, and less ceiling area, which has a higher R value. We're building in a little bit of fudge, so you don't have to add any more. So you square off the ceiling. Basically, what's the difference? What's midway between 8 and 14? It's 11. So we're going to figure this is an 8 by 12 room with 11-foot ceilings. All right, 8 by 12 room with 11-foot ceiling. So we have a higher average wall height. And those are the dimensions we're going to work with when we do our heat loss. So I've got two outside walls now. One is 8 foot by 11 foot and one is 12 foot by 11 foot. And my ceiling is the same footprint as my floor now. In theory, it's going to be 8 by 12. And again, 3 windows, 3 by 5. So let's start. The first thing we're going to do is infiltration heat loss. This is air leakage, all right? This is air leakage. Heated air leaks out over the course of an hour through every nook, cranny, whatever you have in that structure. It's going to leak out, and cold outside air has to leak in to replace it. Our job is to heat that cold outside air up, all right? IBR in its H22 heat loss manual gives us infiltration factors, multipliers that we can use when we are trying to determine rates of infiltration. And these numbers are used based on how many outside walls have openings and based on the type of construction of the house. Again, these are residential numbers, all right? So these numbers represent standard stick frame construction. We're not talking about old farmhouses that are kind of loose. Those have a higher set of factors. And we're not talking about those new structures that are super tight, and every time you inhale, the walls go, you exhale, the walls go woof. That has a lower set of numbers. This is normal residential stick frame construction. And it's based on how many outside walls with openings. It's not how many outside walls, it's not how many openings, it's how many outside walls have an opening, all right? Have an opening. So if I have one outside wall with an opening, I may have two outside walls, but if only one has an opening, that's one outside wall with an opening. 0.012 is my multiplier, and that represents roughly 2/3 of an air change per hour. What that means is, based on studies, which IBR did many, many years ago, based on studies, over the course of an hour, 2/3 of the air in that room will leak from inside to outside, be replaced by the same amount of outside air. We got to heat her up. If I have two outside walls with openings, like our example here, two outside walls with openings, that represents one air change per hour, and the multiplier we would use is 0.018. If I have three outside walls with openings, or I have the main entry, the main in and out of the structure, that's about 1.5 air changes per hour, and my multiplier would be 0.027. Now again, different sets of factors from IBR for different types of construction, right? People say, well, how is this manual J compliant? It may be, it may not be. It's not really, it's a house, okay? We're not flying this thing to Mars, it's a house. But I've used computer software that was where the math was IBR compliant, and for infiltration they say, well, is the house tight, semi-tight, or loose? It's kind of the same thing. It's not what it's the numbers behind the screen that matter, and these are as good as any. All righty, what do those 0.012, 0.018, 0.027, what do those numbers represent? What do they mean? That's a great question, and here we're going to just show you. I'm going to do a mythical heat loss for this little itty bitty room. All right, it's 1 foot by 1 foot by 1 foot. Okay, we want to find the volume. When you want to find the volume of air in a room, it's length times width times height. Okay, that'll tell you how many cubic feet of air you have in a room. So in this case, 1 times 1 times 1, well, that's 1 cubic foot. So the volume of air in this little itty bitty room is 1 cubic foot of air. Now, I have one outside wall with openings. Yes, there are two openings. I'll deal with that later, but it's one wall with openings. So my multiplier is going to be 0.012. How do we arrive at that? Well, remember, one outside wall with openings, we determined that the average air change per hour is 2/3, right? 2/3 of a cubic foot, or 2/3 of the air in that room will leak from inside to outside, be replaced by the same amount of air. Now, if it's 70 degrees indoors and 70 degrees outdoors, I really have no heat loss, right? I'm at equilibrium, same temperature in, same temperature out. Like, it doesn't matter. I don't have heat gain. I don't have heat loss. It is what it is. However, if the outdoor temperature drops a degree, it's now 69 degrees. Technically, I do have heat loss. Technically, I will have heat loss. Over the course of an hour, 2/3 of a cubic foot of 70-degree air will leak from inside to outside and be replaced by 2/3 of a cubic foot of 69-degree air. Now, technically, I have to heat that air back up, all right? What 0.012, that factor that we use, what 0.012 represents is the number of BTUs required to raise 2/3 of a cubic foot of air 1 degree Fahrenheit in 1 hour. So that's where those factors come from. They're BTUs. So 0.018, that's the number of BTUs I need to raise 1 cubic foot of air 1 degree Fahrenheit in 1 hour. 0.027, it's the number of BTUs I need to raise maybe 1.5 cubic feet of air 1 degree Fahrenheit in 1 hour. As we use these mathematically, you'll see how they're used and why they make some sense. Alrighty, so that's where those numbers come from and what they represent. Now let's just do a little bit of math, okay? The math for infiltration is pretty straightforward. Length times width times height, that gives us the volume of air in the room, times your design temperature difference, that's the IDT minus the ODT, it's the spread between those two, times your infiltration factor. So volume of air in the room, design temperature difference, that tells us how many degrees I have to raise that air in 1 hour, times my infiltration factor. It's a way of putting saying, okay, it's 2/3 of the air in that room, or all of the air in that room, or 1.5 times the air in that room. That'll give us it'll help us quantify it. So length times width times height times DTD times infiltration factor. In this case, I have 2 outside walls with openings, so it's 8 times 12 times 11 times 70 times 0.018. Now, any of you little fast-fingered dudes with a calculator, and everybody who's got a phone's got a calculator, you could math that out on your own, couldn't you? You got to see the audience. They're kind of staring at me like, we're eating. Leave us alone. So 8 times 12 times 11 times 70 times 0.018. That'll give us an infiltration heat loss of 1,331 BTUs. So that's part one. We've still got more to go, but that gives us infiltration heat loss, air leakage from inside to outside when it's 0 degrees outside in this particular structure. When it's 35 degrees outside, my infiltration heat loss isn't 1,331. When it's 35 degrees outside, it's 70 minus 35. Well, then my design temperature difference is 35 instead of 70. It's going to be exactly half. My infiltration heat loss will be half of this when it's 35 degrees outside. It would be when it's 0 degrees outside. Heat loss changes with the weather. The colder it gets outside, the greater the heat loss. Alrighty, and there's our room. All right, how are we doing out there, guys? Any questions for us on this so far?
We are looking good, John. No questions so far.
Hot dog, hot dog. All right, now let's do some windows. Windows, everything else we're going to do now. We're getting rid of volume. Everything else is area. Windows, walls, floors, doors, ceilings, etc. It's all area. It's all area. So in this case, I've got length times width times DTD times U value. That's where we're going to use U value, the rate at which we conduct heat from one side to the other. So that's our formula for everything from here on in. Length times width times DTD times U value. Now, as we said before, the U value is a measure of a material's ability to conduct heat. If I know the R value of something, I can find the U value. And if I know the U value, I can find the R value. So if I know the R value and I want to find the U value, I just go 1 divided by R equals U. If I know the U value and I want to find the R value, I do the opposite. 1 divided by U equals R. They are flip sides of the same coin. They are the inverse of one another. So if I know the R value of something, just 1 divided by R is going to give me the U. All right. Now, in this case, with our windows, all right, with our windows, we have three 3x5 windows, three 3x5 windows. And in this example, they are the most common window known to man, the double pane, low E wood or vinyl frame window. If we look at our IBR H22 guide, or we can actually look them up in the manufacturer specifications, we will know that the R value of this window assembly is 2.77, which means it has a U value of 0.36. Now, the cool thing about windows is if they're all the same variety, if they're all the same kind of window, I don't have to do this math 3 separate times. I could, once for each window, if I wanted to. But since they're all the same window and area is area, I could just add up the area of all 3 windows together and count them as one big old window, couldn't I? I don't see why not. That's one of those shortcuts that you can take to make the math a little bit easier. So in this case, 3 15 square foot windows, 15 plus 15 is 30, plus 15 is 45. I have 45 square foot of window area. So now I can just do the math one time and call it good. So in this example, 45 times 70, my design temperature difference, times my U value of 0.36, that's going to equal a window heat loss of 1,134 BTU. So I'm building my heat loss component by component. 1,134. I know there's going to be a question. If it's not in this room, somebody out there in webinar land is going to have this question. And if it doesn't come up now, I know it's going to come up next. So let's get to it. Let's take a look at outside walls now. Okay, we're just building component by component. We've done infiltration, we've done windows. Let's do outside walls. In this case, it's area, but we're not talking about total area. We're talking about net area. Now, why net area? Well, we've already done the heat loss for the windows. I don't have to do that area again. So I just take the net window, I take the window area out of the total wall area. That'll give me the net area. If I had doors, I would have done the same thing. Done door loss, take the door area out of the total outside wall area. So in this case, it's net area times DTD, design temperature difference, times the U value of the wall. In this case, I've got 2 outside walls. I got an 8-foot outside wall and a 12-foot outside wall. Now, I'm no genius, but I know if I were to make that one outside wall, it'd be 20 feet long, right? Because 8 plus 12 equals 20 in almost every state in the union. So 8 plus 12 is 20. They're 11 feet high. 20 times 11 gives me a gross wall area of 220 square feet. Now, from that, I got to take out my windows. I had 45 square foot of window space. I take that out. Now my net area is 175 square feet. So I know 175 square feet is my net area. I know 70 is my design temperature difference. Now I got to find the U value of that wall assembly. Now, again, the IBR H22 manual has charts in the back that you can look up almost anything, and it'll give you a really accurate U value for that assembly. We don't have that luxury. We just know how much insulation is in the wall, right? We said R19 is in the wall. If I know the R value, how do I find the U value? We all know that, right? They're inverse of one another. So 1 divided by R is going to give me the U. So in this case, 1 divided by 19, I round it up, it's going to give me a U value of 0.05. That works. Again, it's a house. We're not flying this thing to Mars. It's a house. So I've got my 3 factors. Net area is 175 times my design temperature difference of 70 times a U value of 0.05. That's going to give me a wall area or wall heat loss of 613 BTUs. So as I continue to build, I'm adding more BTUs to the overall heat loss. Now, somebody's going to have to ask the question, whether it's in here or out there in webinar land, somebody's got to ask the question about not only the windows, but the walls. I guess I'll ask you guys, are we concerned about orientation? Are we concerned whether this wall is facing north, south, east, or west? Does that affect the heat loss? Does the orientation of the walls and or the windows affect heat loss? What do we think? No, it doesn't. That's one of the interesting things. That's what makes heating separate from cooling. Cooling loads, yeah, we are concerned. We are concerned about orientation because of solar gain, right? But when is it coldest out? usually at night, right? And at night it is dark. And when it's dark, the house can't see it. It doesn't know which direction it's facing, right? So, and we don't have a calculation for lunar gain. So when it comes to heat loss, we do not care about orientation. North, south, east, west does not matter to us. If we're doing a cooling load, it absolutely does. But for heating, we don't really care. It's not necessary. Okay, so if you're doing a heating and cooling load, yeah, you have to put an orientation. But the app or the program will only factor the orientation in for the cooling load, not for the heating load. Because again, for the heating load, it does not matter. So that's why we don't care about the orientation of the walls. Is that right? Lastly, let's look at ceilings and floors. Ceilings and floors are interesting. I love this picture. The cable guy was here. This little infrared shows the cold spots, right? Ceilings and floors. IBR has some very specific rules for ceilings and floors. For ceilings, you figure a ceiling loss only if there's no heat above, right? So first floor with the heated, second floor above, you don't have to do a ceiling loss because it's heated up there. Why bother, right? If you're on the second floor and there's an attic above, or in the kind of room we're doing where it's a built up roof and a vaulted ceiling, on the other side of the ceiling is the roof and the other side of the roof is outside, okay, then you got to do a ceiling load then because it's a cold lid. You have to figure that heat loss. So ceiling loads are only done if there's no heat above. If there's no heat above. Floors, IBR will get a little cute on you. And I always put this under the element of, or under the heading of, do what you have to do to sleep at night. Some people kind of get a little weird with this, and I understand it, but I also understand what IBR is trying to tell us. Obviously, if you're second floor and there's a heated first floor below, do you have floor loss? Of course you don't. You don't have any floor load, so you don't have to do a floor heat loss because it's warm down there. Not going to lose any heat through the floor. How about over an unheated basement or an enclosed crawl space that's like a mini basement? Do you have to do a floor loss then? IBR says no. IBR says it's not necessary for one simple reason. It's not 0 degrees in that basement. It's more like a constant 55. And if you were to do a heat loss calculation, 70 degrees in this room, 55 down here, that's a design temperature difference of 15 degrees. You'd come up with a heat loss number so insignificant that it would be more than offset by a person walking into a room, because you by yourself give off about 400 BTUs just sitting there. So that's kind of why they said, it's not necessary. Do what you got to do to sleep at night. I absolutely understand that, but think about what you're doing and why. If you're going to do it, 15 degrees, make it a 15-degree design temperature difference. Don't do 70 because that's not accurate. Now, if it's an open crawl space, right, and ventilated, where the temperature in the crawl space is close to the temperature outside, oh hell yes, do a floor loss. Absolutely do a floor loss. If it's a slab, yeah, you got to do a floor loss on a slab, even if it's insulated. There's going to be some downward loss, an edge loss. So you've got to do slab. You got to do a floor loss when there's a slab. But over an enclosed basement, especially if you got pipes running in the basement and everything like that, IBR says it's not necessary. Do what you have to do to sleep at night, but understand what you're doing and why. Now, for us, we're just going to do a ceiling load. And again, length times width times DTD times the U value. Remember, we had R38 in the ceiling. And if we divide 1 by 38, we get 0.03. Math that out, 8 times 12 times 70 times 0.03 gives us a BTU load of 202. Not much of an upward load either, but it's well insulated. So now I've got everything I need. I've done heat loss. So infiltrations 1331, windows 1134, walls 613, and ceiling 202. I add them together and I come up with 3,280 BTU heat loss for that one room. Now with that number, I can start thinking about how I'm going to heat that room. All right. If I've got baseboard that's rated at 500 BTUs per foot at 180 degree or 170 degree average water temperature, okay, 500 BTUs per foot, it's going to be about, probably I'll put in a 7-footer, right? That's 3,500 BTUs, close enough. I could take a few fins off if I'm really over officious, but we could leave it as is. Put a 7-footer in there and we call it good. Okay. Or if we have radiators, we'd look up the output of the radiators, radiant floor heating, we'd figure out tube spacing and installation method, etc. But it all starts from knowing what that number really is. Very good.
John, let me interrupt you just for a second here. We've got Tim out here in Alaska asking about houses built on stilts because of permafrost. Houses 2 feet off the ground with wind chills of -50. No heat loss.
By golly, you have floor loss there. Yeah, that's a cold surface, my man. Absolutely cold surface. Now, I'm glad you asked that question for the guys in this audience that can hear. They asked about wind chill. Do we worry about wind speed here? Does wind speed affect infiltration, heat loss, and things like that? It absolutely does. It absolutely does. Now, those infiltration factors I gave you, 0.012, 0.018, 0.027, those were arrived at based on a long-term study between IBR and the University of Chicago's Building and Science Department. And what those numbers assume certain things. And one of the things that they assume is they measure air leakage based upon a 25-mile-an-hour wind consistently, not gusting, but a steady 25-mile-an-hour wind blowing in all 4 directions at the same time. I'm not entirely sure how that would happen, and I'm not entirely sure if it did which way your hair would blow. Okay, for some of us, it's not an issue. For me, it's becoming less of an issue with each passing day. But yeah, a wind is built in, so we don't have to factor anything excessive in. If it's gusts are one thing, but a 25-mile-an-hour steady wind in all 4 directions at the same time is probably a tornado or something like it. But that part's built in. If you feel the need to add in more, again, you got to sleep at night, right? Especially up in Alaska, you still got to sleep at night. But that's given to you automatically, that level of wind. I don't know if that answers your question, but and let us know. But that's how wind chill is built into the program. Anything else out there, Jason?
We're quiet out there in webinar land.
Hot dog.
Must be doing a good job.
Either that or I got the whole audience sound asleep. I'm not sure which one it is.
Right.
So some takeaways, or as we like to call them here in Cranston, takeaways. Like that, I thought of that myself. The audience, you got to see this audience. They are stunned.
Just flatlined.
No, they're not flatlined. No, they're stunned. I'm looking at this group. This is not a flatline group. This is a group that's on the edge of its seat, excited and happy to be here. Am I right? Well, maybe not. I don't know.
You're not selling it, John.
I'm not selling it. All right. There you go. Simplify where you can. That's the important thing. Simplify where you can, but don't be simplistic. Again, 35 BTUs a square foot is finished carpentry with a sledgehammer. It works, but what are you doing, right? What are we here for? Because a marginally competent handyman can still go 35 BTUs per square foot and do it for just as easily as you can. So why hire you? Hire you because there's a level of professionalism expected there. So simplify where you can, but don't oversimplify. Do it the right way. Really, there's no need to add fudge, because if you follow this along, there's a lot of fudge built in with that 25-mile-an-hour wind speed in all 4 directions. That's some built-in fudge, right? We squared that room off. That's some built-in fudge. You have a boiler that you have 57,000 BTU heat load. You put in a boiler that's got 70,000 BTU output. You've got fudge. There's no need to add extra. Although the urge to oversize is powerful, right? The urge to oversize and give it a little extra just to be safe is powerful, powerful stuff. And if you do that, if you add a little bit here and a little bit here and a little bit here and a little bit here, it turns into a lot. And now we've got a grossly oversized system. As we said, wall and window orientation doesn't matter for heat loss. Heat gain, it does. Heat loss, it doesn't. So we don't have to worry about that for heat loss calculations. As we said, that wind is accounted for to the degree specified, and ceilings and floors only do those when necessary. Again, heat above, no need for a ceiling loss. Heat below, no need for a floor loss. Over a unheated, unconditioned basement, well, you got a call to make. Just understand what you're doing and why you're doing it, and whether this is the right thing to do. Most cases, if it's an enclosed basement, it's really not necessary because it's not 0 degrees in that basement, right? It's more like a constant 55. So you make your decisions as best you can. All righty. Well, that does it for Takeo Tuesday. Jason, any last minute questions out there that we could?
No, I think you must have covered all the material well, because there isn't a lot of chatter out. We've got quite a few guests with us, but not a lot of chatter out there.
Well, how about that? Yeah, I guess we must have simply amazed. And I see Chris actually says that.
Yep.
We are just amazed.
We're
Or amazed, either one.
Yeah.
All right, well, cool. Hey, again, last call for questions out there in webinar land. But if there are any, type them on in. If not, we're going to say thank you, and we appreciate the gift of your time today on Takeo Tuesday. And this coming up weekend, Jason, if I'm not mistaken, this is Labor Day weekend, correct?
That is correct. Yes. Monday is a holiday.
Monday is a holiday, so I won't call you and ask you what you're up to then, Jason.
Yeah. Well, let's get together soon.
All right. Yes, we will. We'll definitely get together soon and catch up. But thank you all to everybody out there in webinar land. Appreciate the gift of your time, and let's make sure we have a great holiday weekend. Be safe out there. Enjoy yourselves, and so we're all back to work ready next Tuesday. So thank you all. We're going to sign off. I've got to get to my class. They're all here staring at me, wondering what the hell's going on. But anyway, thanks again, and take care.
Sure. Bye-bye.